Hey everybody, in this video I'm going to teach you how to use percent abundance values to calculate the average atomic mass of elements. Before we do that, let's remember some things like not all atoms of a given element have the same mass. In prior videos of this series we've talked specifically about carbon atoms. Like some carbon atoms have a mass of 12, while others have 13, others 14. They're all carbon because they all have 6 protons. But of course, you can still be carbon with different numbers of neutrons. Here, 6, 7, and 8. There's even a name for atoms like this. They're called isotopes. And you're looking at the 3 naturally occurring isotopes of carbon. When you look at a periodic table symbol for carbon, you'll see 2 numbers there. The 6 makes sense because that's carbon's amount of protons that it always has. But the mass that you see on the periodic table is a decimal. And on the periodic table, it's a decimal because the periodic table is taking an average of all the different masses that this element can have. For carbon, or in carbon's case, sometimes 12, sometimes 13, and sometimes 14, and it averages all of those out to get 12.011. So that's why those masses are decimals on the periodic table. To understand how to perform this calculation, you first need to know about something called a percent abundance. This is a number that shows just how common, or abundant is the word that they use in the name of it, in this term here, just how common each isotope is. For example, we'll keep going with carbon. Carbon's percent abundance, or carbon 12's percent abundance, is 98.9%. What that means is almost all of naturally occurring carbon, 98.9% of all naturally occurring carbon, has a mass of 12. It is the most abundant of the isotopes by far. Carbon 13 has a much lower abundance. Only about 1.1% of all carbon atoms have a mass of 13, and that leaves essentially nothing for carbon 14. Its percent abundance is less than 0.0001%. If you know these percent abundance values and you know what the naturally occurring isotopes are, you can use that information to calculate the average atomic mass of an element yourself. And that's what we're going to conclude with in this video. One thing to know before we get to that, however, is that because each of these isotopes has its own unique percent abundance value, you need to know that there's a special type of average called a weighted average that you have to be aware of in order to perform this calculation. And that's really what I'm teaching you in this video, is how to calculate a weighted average. We're going to do 2 examples. The first one dealing with copper, and I'm going to walk you guys through that, and then we'll look at a second example that you can try yourself. Let's take a look at it. This says that copper has 2 common isotopes, copper 63 with a mass of 62.9296, and copper 65 with a mass of 64.9278. So we know what the 2 isotopes are, and we are given their exact masses. It then goes on to say that copper 63 has a percent abundance of 69.09, and copper 65 has a percent abundance of 30.91. So the first thing you're going to do to make this calculation is list out all of the masses of all the isotopes you've been given vertically. That's why I like to set it up, at least, and I recommend you do the same. We'll start with copper 63, and the exact mass of a copper 63 is 62.9296. So we'll list that out, and then beneath it we'll do copper 65's mass, 64.9278. So that's step 1, just listing them vertically. Here there's only 2 isotopes, sometimes you might have a lot more. Again, you're just listing them out. The next thing you're going to do is multiply each of those masses by its corresponding percent abundance, but with one really important change. Let me switch colors to show you that. You're going to take the percent abundance, find the decimal point in that percent abundance, and you're going to move that decimal point 2 digits to the left. So 69.09 becomes 0.6909. That is turning what's called a percent abundance into a relative abundance. Essentially, it's the same percentage, except instead of out of 100, now it's just out of 1. So we're going to do that again for copper 65's percent abundance. Here's my decimal, 2 places to the left, so this gets multiplied by 0.3091. So I've multiplied these numbers and written down the answers that my calculator gives me. Notice I'm not rounding yet, so I want to use as many decimal places as possible. We're going to only round the final answer. The last step, once you've multiplied all of your masses by their relative abundance values, is to take those answers and simply add them together. That's why I like to list things out vertically, so then I can write this as if it were one big giant addition problem. Here, I've just got these two numbers to add. And I get 63.54724 when I add them together. That is my answer. That is my average atomic mass, my weighted average atomic mass of copper, factoring in their various percent abundance values. There's one final step, of course, which is to round this properly. If you look at the numbers that we used to make this calculation, the masses themselves had lots of digits, lots of significant figures there. But my percent abundance values only had 4, so I'm going to round my answer to also have 4 sig figs, giving me 63.55 as my official final answer. So here's our next and final example dealing with magnesium. The best way to do this is for you to pause the video and try this yourself before watching me go over the answers. One thing to note here, in a slight difference to our last example, is that we weren't provided with the exact mass of each isotope. I only know it's Mg24 with its percent abundance. You can do the same calculation, you'll just use the 24 multiplied by that modified percent abundance. So assuming you've tried this yourself, or if you just want to watch me do another one, my first step is to list out all of the masses. In this case, there's 3 of them, 24, 25, and 26. I'm going to multiply each of those masses by the modified percent abundance. So 78.7 becomes 0.787, 10.13 becomes 0.1013, and 11.7 becomes 0.117. Those are my relative abundance values. If I multiply those, I get the numbers shown here, my final step being to simply add those together, which gives me 24.4625. Here I'm going to round this off just like last time. It looks like some of my percent abundance values have less sig figs, so let's go to just 3 places this time. 24.5 as my final calculated weighted average atomic mass. I'll close the video by pointing out one last little trick that you can use to check your work, and that is remembering that the periodic table, it already has these average atomic masses. We're sort of just confirming what is already known. So for magnesium, I can see that its average atomic mass is listed here as 24.305, which doesn't match exactly the 24.5 that I got, but it's pretty close and tells me that I likely did this work correctly. It doesn't match as closely as what we see on the periodic table in this case because the masses I used, 24, 25, and 26, were not the exact masses of each of those isotopes. If I go back and do the same check with my copper calculation, and with the copper we did use the exact masses of 62.9296, you'll see that in copper's case, remember we got 63.55, and this matches almost exactly with what we find on the periodic table. So either way, knowing that you can check a periodic table to see if you did a good job is nice to know. That also wraps it up for this video on calculating average atomic mass. Thanks a lot for watching.